All right. Well, like you said, we need another grade. So let's get you one. We'll have a test. You can do it before midterms, right? We did October 1st. That's a week from today. I'll tell you exactly. You're going to know exactly what's going to be on this test. So we're going to do, what are we, astronomy?
Yes.
Okay, very simple. It's going to be this. Done this a bunch. We're going to keep doing this. This does not go away, right? So, what is this? Well, the main sequence is part of this. Have I not given you the name of this yet?
No.
It's commonly called the Hertzsprung-Russell diagram,
Wow.
or the HR diagram, which is called the HR diagram. Okay. HR diagram. Let's try to do this from memory, okay? All right. What's on my HR diagram? What are we plotting? What's on the main sequence? Like, what are the individual plots and points? Stars, okay? So this has to do with stars. It's a graph, it's a chart showing stars. What's it telling me about stars? What can I determine for this? Size? Temperature? What else? Luminosity? Good. What goes on my y-axis here? Luminosity. Luminosity, of course, is its intrinsic brightness. So, if not like, you know, part of the thing of brightness is how close it is to me. But another thing of brightness is just how bright is it if they were at the same distance from me, right? So this is, when we talk about luminosity here, we're not talking about how bright does it appear from Earth. We're saying how bright is it, period, right? And brightness of a star comes from how much energy it's putting out. You've heard of a 20-watt light bulb, a 30-watt light bulb, a 50-watt light bulb, right? Watt is a term of energy. So a 20-watt light bulb is putting out 20 watts of energy. A 50-watt light bulb is putting out 50 watts of energy. Which one's going to be brighter? Say 50. Yeah, 50 is bigger than 20, right? So it's actually more than twice as bright as a 20. It's similar with stars. If I had a star down here and a star up here, I mean, the star up here is going to be like twice as bright. So as I get to the top, I should expect stars to be brighter, right? And so one of the things with luminosity is it's going this direction, okay? What's on my x-axis traditionally? Temperature, okay? And this is an inverted axis, right? You've got to remember that. So temperature runs this way. Okay, so we've got luminosity, and we've got temperature. Now, most stars appear on what we call the main sequence. This is not the graph of the main sequence. The main sequence is a section of this graph, okay? I know that you're associating those two things because it's really all we've talked about so far is the main sequence. So our main sequence exists basically, don't draw this, but it exists basically like something like this, right? Stars appear something on this kind of a plot along this. What kind of stars appear up here? Big or small?
Big.
Big. Right, so maybe I get a big star up here. Big stars, just by the fact that it's up here, that tells me two things about a big star. It's very hot and it's very bright. Down here, I've got what kind of stars? Small stars, right? And based on the fact that it's down here, I know that it's relatively cool and relatively dim, right? Okay? Of course, stars appear all along this thing. Now, right now I'm only kind of showing like one star at a time, right? You guys are given a chart like this. Even that doesn't really do it justice. If if we were to graph like all the stars, would there be more up here in the big stars or more down here in the little stars?
What do you have to do?
If we were to take just like a picture of the night sky, just in a certain field of view, right? Would you expect there to be a lot of big bright stars or a lot of small dim stars? There's a lot more small dim stars, okay? Like a whole lot more, okay? So this doesn't represent like the relative numbers of stars. This is just, all we're seeing here is the luminosity and the temperature, right? So there's, of course, some other characteristics, right? What color star is this going to be?
Blue.
Blue, right? What color star is this going to be? Red. What color star is going to be kind of in the middle? Right, there's that yellow and then orange, right? Okay, good. What's happening over here?
White, green.
Not green, there's no green.
White.
White. Okay, I might want to move my orange over a little bit. I'll put my red over here too. Let's go orange. Red, kind of like the rainbow, except no green. Instead, we have white. Right? Okay. Now, we'll keep it simple for this one. All right. Then we have classifications. Classification goes. We watched a video on this. The folks who first started doing this, cataloging these stars and looking at brightness, they were looking at the brightness of, particularly of the hydrogen absorption line, and they looked at the ones that had the brightest hydrogen absorption line, and they called those A-class stars, all the way down to the ones with the dimmest. The problem is, that's not the most accurate representation of how bright a star truly is. It only shows how much hydrogen there was that was being absorbed. They came up with a system A through, M and G, all these letters. And then somebody else came along and figured out like, oh, that's actually wrong. And so we need to make a change there. And so they put them in what we now recognize to be the proper order. And you need to know these. What class of star are the blue stars?
A.
O.
Oh, sorry.
These are O stars. Anybody remember that acronym that they gave?
Oh,
That little mnemonic device?
What
O.
about Obama?
OB.
You could do Obama if you wanted. O, B,
AFG.
Obama, gay.
KM.
O, B,
I forgot that's it.
A, F,
Obama,
G,
Right, A.
K, M. O, B, A, fine girl, kiss me is the one that they had. You gotta know that, okay? You must know that. You've gotta be able, I'm just gonna give you a line, or a, graph. This will be the test, okay? Fill it in. Give me some relative sizes. Show that these are bigger than this. I'm not saying you gotta be perfect, but your blue stars need to be bigger than your red stars. Tell me colors. Tell me the classes. Label your graphs. Label your axes. You must be able to do this. I'm telling you exactly what I'm going to give you just this. And I'm going to tell you what to do. Draw the stars in their relative positions by their relative sizes. Label color. Label classifications. Tell me what's on the x-axis. Tell me what's on the y-axis. You must be able to do this. Okay? I'm going to count this for as many points as your last test. You know exactly what's on it. Okay? And I'm not pulling any punches. This will be the test. You will study and you will know it, or you won't. Right? Any questions? Yeah? Oh, we still have more to put on here though, don't we? Go ahead, what were you asking?
No, I wanted to ask, so the sun is a G-class star,
Yes.
but yellow stars are like right in the middle. Why is it not like F? So how do you know where to put the O, P, A, F, G, K, M.
Brother, if you're close, I'm happy. If you're close, I'm happy. It'll be great. I'm going to look, these are in the relative order. I'm going to look, these are in the relative order. I'm going to look at that's getting bigger. I'm going to look at that's going this way. This test, you don't have to explain anything to me. You just have to be able to do this. Okay? All right. Yeah, so next, down here we've got white dwarfs, right? Because they're on this side, what do they have to be? Look at where they're at. What do they have to be? They've got to be very hot, but not very bright. Good. And then we've got some stuff over here. All right. What are these? Red giants. Or giants. And so they must be very bright. They're not very hot. Not relatively speaking, right? These are all stars begin their life somewhere on the main sequence. By the way, they don't grow bigger. Generally speaking, stars don't grow bigger. As they do nuclear fusion, they actually get smaller. Okay? Because they lose mass, right? Mass gets converted into light and neutrinos and stuff like that. So it's not like a star starts off as a baby star. You know, I got a 1-year-old. This kid's a monster. He's going to be huge. We keep feeding him. I mean, look out, he's going to be huge, way bigger than you. We just keep feeding him, and he's just, he looks like a 3-year-old or something. And tackles like one too. Go headbutts. It's dangerous. So, but stars don't do that. Wherever a star starts, that's where it starts. But then as it runs out of hydrogen to fuse into helium, it expands. And so it leaves its spot on the main sequence, and it becomes something like this, right? And then after it's done doing the next stages of its life, it will typically, many of them will have an explosion, and they'll become a white dwarf. So you don't have to know this for this test. For this test, you just have to be able to do this. But the idea is, wherever it was, it will go to something like this, and then it will go to something like this, right? So like step 1, step 2, step 3. There are other things that are not on this diagram. We're going to talk about them today. Okay? Can you do that? Great. This is a good chance to get back in the game, brother. If anybody knows another girl who came like 2 days ever, tell her, like, you can get back in the game, but you got to come see me. I'll work with you. All right. I want to show y'all something. Let's see. Can you guys see this? I'll recreate this on the board, okay? Okay, so this is looking at stars within, 30 light years of us? I think it says it on here. 21 light years, okay? So I'm going to make this chart. This is new stuff, right? So this is notes. Stars within 20 light years of Earth. Okay. I'm going to do this. I'm going to go O, B, A, F, G, K, M, white dwarf, and brown dwarf. I'm going to expand this chart beyond theirs, okay? So this is the class. This is going to be the count. see when you look at this so far? Yeah, I mean, it's represent what we got there, right? I got my brightest stars, my bluest stars up here. We've got my dimmer stars down here. These have more mass, right? These have less mass. These are off the main sequence. I guess we could even add in giants or supergiants. So within 20 light years of Earth, there are exactly 0 blue stars. There are no B-class stars. There are no A-class stars. So we don't have a single... Oh, I'm sorry, I take that back. There are 2 A-class stars. So we start to get some white colored stars, large white stars here. We've got just 2 of them, but none of these huge ones, right? Then you get to the F. So now we're starting to trend more, yellowy to orange. And F, we've got 1. G class, that's like our sun, there's 7. K, that's going to be moving towards the orange, that's going to be 17. M class stars, these are the red ones, 94 of them. White dwarfs, there's 8. Brown dwarfs, we found 33. And there's none of these. So how do I interpret this data? What's this telling me? Graph this data. I'm going to plot a point for every one of these, okay? How many do I put for white star or for blue stars?
0.
Oh, how many for B class stars?
0.
How many for A class stars?
2.
2. I'm going to put 2 points. How many for F class stars? 1. How many for G class stars? 7. 1, 2, 3, 4, 5, 6, 7. How many for K class stars? 17. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. How many for M class stars? 94. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Wow. Okay. If you really think I counted every one of those, you're gold. All right. How many white dwarfs? 8. Brown dwarfs, which aren't even on this chart, how many? 33. So I gotta put them down. They're not even on here, but I got 33 of them. Put them over here. And exactly how many of my giants? None. 0. Okay. So when you see it like this is just this, but visual. What do you see? What are the dots telling you?
Way more red.
Way more red stars than anything else. What else did it tell you? Yeah, the smaller stars are way more abundant. Way. It must be a lot easier to make small stars than it is to make big stars. Now, these are the remnants of some big stars. Maybe there used to be some big stars, right? These stars used to be these stars, right? But they're gone. We don't have any black holes in our neighborhood either, by the way, so we definitely never had any of these, right? These are pretty rare. These are, stars get much more common as we move down here. We have found 33 of these, but we expect to find a lot more. They hypothesize that there are probably as many brown dwarfs as there are all other stars combined. Okay? You want to know that.
How do they figure that?
Give me 1 second. They figure that because there's a trend. Very few of these, lots of these. There's enough mass to make small stars, but if these are so small, I haven't defined a brown dwarf for you yet, have I? Go ahead and finish this, and I'll talk to you about a brown dwarf. Yeah, brother. Draw it. Write it. Catch you up to speed real quick. We're going to do a test in 2 classes. It'll be on October 1st because we need it. Because we need another grade in before midterms. I'm going to make it worth as many points as the last test was. And it is to literally do the HR diagram here. Okay, so I'm going to give you just the axes. You're going to label luminosity with an arrow, temperature with an arrow. You're going to fill in the classes. You're going to fill in the colors. And then you're going to put the stars with a relative size. So what I mean that relative size, I mean like these just need to be clearly bigger than these and than these, right? So relative size, relative location. I'm not looking for perfection. Just show me that you get the concept of where those things go. So this test will happen on October 1st. If you're an athlete or whatever, it'll save you bacon, right? That's the goal. Everybody else, it'll be good. It'll help us. I'm not going to ask you any analysis questions off of it, but those will be coming, right? But for this test, you've just got to be able to graph this. What we're doing right here is this is a chart that shows, and this is the same chart, that shows the relative number of these classes of stars within 20 light years of Earth, right? And so I asked everybody to kind of analyze this, tell me what you see. Nobody told me anything. So I'm like, all right, let's draw this river. And then tell me what you see. And then at that point we saw like, okay, there's a lot more small stars than there are big stars, and there seems to really be a trend. Staying on of a trend, okay? If we're getting bigger as we go this way, and a lot bigger, right? Like exponentially bigger. Yes? Can you see that? I mean, we're really getting a lot bigger as we move down. Well, these are the smallest actual stars. But there might be a whole lot of things that never got big enough to start nuclear fusion. They never actually became what we would truly classify as a star. There might be a lot of them. In fact, if there's 90 some here, you might expect like 200 down here, okay, on a linear kind of progression. Those are what brown dwarfs are. They're stars that they almost became a star, but they weren't quite big enough to start nuclear fusion. Okay, they're still hot. They're massive. They're bigger than Jupiter. Or Saturn, they're huge, lots of gas, lots of heat, lots of, and so they glow a little bit, but they glow in radio waves, or they glow in infrared, light that we can't even see, lower energy light, right? Think about your electromagnetic spectrum. You got X-rays, or excuse me, you got gamma rays that are the highest, and X-rays, and you got UV, and then you've got the visible spectrum from violet on down to red, then you've got infrared, then on down to radio waves, which are super long. The longer the wavelength, the lower the energy. These guys, you can't see with the naked eye. They're operating in infrared. They're harder to see, is probably why we've only found a few, relatively few of them. But we suspect, based on the trend, there should be a lot more of these out there in the universe. Okay? All right. Questions about what you've seen so far? Okay. Well, let's do the next thing.
A brown dwarf is something between a star and a planet. Up at the night sky, planets and stars look the same, but when observed closely, they are very different from each other. Stars shine by producing their own light through nuclear reactions, using the energy stored in the tiny nucleus at the center of atoms. But planets don't have enough mass to produce energy by nuclear fusion, so they shine by reflecting the light of their parent star. By understanding what makes some objects shine by themselves and others reflect the light of some other body will allow us to understand brown dwarfs as well. Brown dwarfs are stars resembling planets. They are
Let's pause. Expect, not this test, but the next one. Expect to see this question. What is a brown dwarf? Okay. I'd write this down, okay? Well, he just gave you one definition of a brown dwarf. He said, number one, it's a failed star. Failed star. What does that sound like it means? Okay. What are the thoughts? What if I said I was a failed soccer player? What would that tell you about me? I wanted to be a soccer player, but I'm not, right? Maybe I didn't have what it takes. Maybe I went out for the team, but coach wouldn't put me in the game. So a failed star wants to be a star. It wants to do, what's a star made out of? Yeah, like 75% of it is hydrogen gas. They're made out of the same stuff as stars. What's happening inside of a star? Fusion. This didn't have enough hydrogen, and so it didn't have enough gravity so that fusion ever started. Okay, so that's what we want to say. Failed star. Number two, not enough, I'm going to say mass. You can write down hydrogen if you want. To start nuclear fusion. They got close. They weren't quite big enough.
too massive to be planets, but not massive enough for hydrogen atoms to fuse in their cores and become stars. Objects smaller than 10 Jupiter masses are planets. Larger than 90 Jupiter masses are stars. Meanwhile, brown dwarfs are just in between, sharing properties similar to both.
Okay, that's another thing we want to know. They're kind of somewhere between a planet and a star.
These objects form just like stars, but their small amount of energy comes from the heart stored in them during the collapse of the parent gas cloud from which they formed. So, unlike stars, brown dwarfs gradually cool and fade as they age, emitting infrared light. Because of their low temperatures and small sizes, they are very difficult to observe. best way to find them is by using infrared telescopes, which can detect the heat from these objects even though they are too cool to radiate visible light. Brown dwarfs were only a theoretical concept until they were first discovered in 1995. Astronomers now think there might be as many brown dwarfs as there are stars. Understanding the formation of brown dwarfs is essential to understanding that of planets and stars. When NASA launches the James Webb Space Telescope, we will be able to learn way more about these exotic worlds.
Stop there. So a question that you should count as coming is, what is a brown dwarf? Right? It's a failed star. Doesn't have enough mass to start nuclear fusion. It's somewhere between a planet and a star. Right? That could be an essay question. That could be a multiple choice question. All right. Look at everything you see. Hypothetically, what is the most numerous type of star in the galaxy, in the universe? Take a look. Theoretically, which one's the most numerous? Brown dwarfs. Theoretically, they're the most numerous. Write that down. We keep calling them stars. Are these actually stars? No. To be a star, you must be doing nuclear fusion. You must. These can't because they're not big enough. How'd your arm go, by the way? How much more you got in that?
6 weeks. 5 or so.
At first you were saying you thought you'd be out pretty quick, right?
Yeah.
I was like,
Say 6 days.
Yeah, I thought that. The doctors. I mean, if it was me, I'll be out there.
brother, I'm seeing that thing and I'm like, that's not a 2-week injury. Not with that. They don't give you that for 2 weeks. They give you an ace bandage.
Autobahn.
You said he looks like an Autobot? All right. So theoretically, what's the most numerous object star in the universe? Brown dwarf. What's the second most numerous? You're going to be wrong. Doesn't matter what it is because you don't know this one yet. Okay. All right. You were thinking right. You were definitely thinking right. No doubt about it. That was a lead into what we're doing next. Okay. So, first question is, what is, and you already know this, what is the most numerous star type? Right? And you know that it's a brown dwarf, right? Now the second is this. What is the second most numerous star type? You ready for this? A binary star system, or a binary star. That'll be a question at some point for you. A binary star. What does binary mean? Two. These are two stars that are together.
Actually, not mine.
You're at the wrong school, then, brother.
He knows a lot about science stuff.
guy's legit.
Our solar system has just one star, the Sun. But this is actually a bit uncommon in the galaxy. A greater percentage of systems are multiple star systems, meaning that their systems contain two or more stars, and in particular, binary star systems.
Did you catch that? So our sun exists as a single star, but more numerous than any single star are binary star systems. Right? If we've got, make up a number, if I've got 20 trillion individual stars out there, okay, of varying colors and all that, then I'm going to have more than 20 million binary star systems out there. It's far more frequent that you'll encounter two stars together orbiting each other in some way than you will one star hanging out by itself. That's kind of different, isn't it? I didn't expect that. Did you expect? I knew about binary stars, but it was not in my head that, oh, actually that's the norm, is that two stars would be together, okay?
Which specifically contain two stars, are exceptionally common. When we can see both of the stars, they are called visual binaries, and if the plane of their orbit happens to coincide with our line of sight, such that they pass in front of each other, they are called eclipsing binaries.
Okay. So we had, just gave us some stuff here. We had visual binaries. And then eclipsing binaries. So visual binary stars we can actually see. You can look up and you can see, hey, there's two stars. They're separate. Other times you can't. The stars are so close together that we do not even come close to having instrumentation to be able to see that they're different. We can detect that there's a difference, but we can't see it. So a visual binary star means that basically with technology, we can see that there are two distinct stars. An eclipsing binary system. We'll talk about that in just a second. It's going to be you. Doing my best, but I don't know what to tell you. Here's you. You're looking out. Okay? Whenever I have two stars, we're going to see in a little bit, it's not like one goes around the other. They influence each other. You're used to thinking of just one thing going around another. Like you think about our Earth and you think about the moon and you think to yourself, well, the moon goes around the Earth, right? I mean, it does something like this. You don't think about the Earth going around the moon. Relatively, it doesn't. But the gravity of the moon does impact the Earth. It causes it, it pulls it to where they are actually both going around some point in between the Earth and the moon that's a lot closer than the Earth. You think about the sun and you think about the Earth. You think about the sun going around the Earth. You don't think about the Earth. I'm sorry, you think about the Earth going around the sun. You don't think about the sun going around the Earth. But actually there's this point in between the two of them that's not at the center of the sun. It's, maybe a mile from the sun. It's in the sun because the sun is so much more massive than the Earth. But the gravity of the Earth and of Jupiter and all these other planets does impact the sun, and it's moving, okay? Same thing with these star systems. It's not like one star goes perfectly around another star. They impact each other. Well, if they're impacting each other, if they're relative to where I'm looking and where you're looking right now, if it's like this, then you always see the two stars, right? Look up, just humor me. I know this is silly and easy, but if the compared to the plane of my view, if the two stars, and I probably better do this on camera, or whatever, compared to the plane of my view, I can always see these two stars, right? But now if these stars are operating in the same plane, now you can see two stars, but now you can't. Now you can, now you can't, now you can't. Like one would eclipse the other as they're moving, right? Does that make sense? So the difference between an eclipsing binary star and all other binary stars is not like, oh, these eclipse and those don't. It's just, it's from our point of view. That's it, okay? But what happens in an eclipsing binary star is that they pass in front of each other. So imagine I got two lights here, right? Tell me when it's at maximum and at minimum brightness. Ready? Set. And I've got two lights shining right at you. Is it at maximum or minimum? Ready? You gotta say something.
Maximum.
Minimum? Because one's blocking the other, right?
Maximum.
Maximum. I got two lights on me. I got one light on me, two lights on me, one light on me. And so literally we can see as you watch these stars over time, you know, it's not happening like in a second here, right? But they'll get brighter and dimmer, brighter and dimmer, brighter and dimmer. As they pass side by side, they're brighter. When they're lined up, they're dimmer. Brighter, dimmer, brighter, dimmer. And we've seen this with some stars since the beginning of time. I mean, people have looked up and noticed that star gets brighter and dimmer from season to season. They didn't know why. Nobody can see. So far away you couldn't see there were two stars there that are orbiting each other. But that's what's happening in an eclipsing binary star. That's what he's showing here. That's what this graph is, okay? This is the maximum brightness. So up here, is this when they're side by side or when one's in front of the other? This is side by side because this is brightness, right? So this is brighter. So this is side by side. This valley here is when they're eclipsing each other. And then I'm back to side by side and then eclipsing. Now in this case, one star is a whole lot bigger than the other. And so when the star that's bigger is behind the one that's smaller, we get a huge dip in brightness. But when the smaller one's in front of the bigger one, we get a small dip in brightness. Does that make sense? Okay. Let's get at it.
This situation allows us to gather important information about the system and is actually one of the best ways to detect them in the first place, as we can chart the reliably periodic change in luminosity first as the larger star passes in front of the smaller, and then as the smaller star passes in front of the larger in cyclical fashion. But beyond this, we also know that stars come in many different varieties. Therefore, the possible combinations that exist for the two types of stars that comprise a binary system are even more numerous. What are the most interesting combinations we have been able to find for types of binary star systems, and what can they teach us about the universe? Certainly, there are many binary systems that involve very sun-like stars orbiting each other at quite a distance. An example of this is Alpha Centauri A and B, which we examined in a previous tutorial. But a far more interesting case involves close binary systems. This is when the stars are very close together, orbiting around their center of mass quite rapidly. Sometimes they are so close that the gravitational distortion produced causes their stellar atmospheres to exchange material, or they can even be so close that they are in direct contact with one another, such as this system with two large, hot main sequence stars practically overlapping. This is most fascinating when one star is a compact object, like a white dwarf star, neutron star, or black hole, as this object will begin to pull matter away from the other object in the system until a dramatic event occurs, causing the accretion of gas from another star. It becomes a cataclysmic variable star, where the incoming gas gets very hot and emits radiation. We sometimes call such an object a vampiric star, as it is almost as though it is sucking the essence out of its companion star, like a vampire. If instead the compact object is a neutron star or black hole, this is called an X-ray binary, which can be either a low mass or high mass X-ray binary, depending on the mass of the donor star, which is the other star in the system feeding the compact object with material. One fascinating binary system is called AR Scorpii. This is a binary pulsar, which consists of a white dwarf pulsar about the size of Earth and a red dwarf star. Pulsars are highly magnetized jets that emit powerful beams of radiation in a rapid periodic manner. Typically, pulsars are neutron stars, but sometimes they can be white dwarfs as well, though being much less compact than neutron stars, they rotate more slowly. AR Scorpii contains the first object of this type that was ever discovered. We should note that binary systems can have complicated evolutions. Take, for example, a binary system with two fairly large main sequence stars, which form with around 15 and 20 solar masses respectively. We know that stars of this size evolve rapidly, since the inward gravitational pressure is so strong that fusion occurs at a furious pace, burning through the
Let me translate that. On this diagram, this is not on your test, but this is something to know. You know, we got our blue stars over here, we got our red stars over here, everything in between, right? Which stars last the longest? The blue or the red? Blue. You ever light a fire? And like you light a small fire and you light a huge fire. Just, which one burns hotter? Like just on a fire in your house, if you in your backyard, or whatever. Which one's going to burn hotter, a small fire or a big fire? Big fire. It's going to burn a lot hotter, right? It's also going to burn a lot faster. A lot faster. Because it burns so hot, it's going to burn, it takes energy, it takes fuel to make that fire so hot, right? So it burns through it a lot faster than a small fire. It's the same idea here. These guys are blowing through hydrogen much faster than these guys are. So you form a blue giant up here, it's going to go from blue giant to, to here and to supernova and everything very rapidly. A red dwarf is going to last a very long time. A brown dwarf even longer, because they're going through hydrogen much slower. They're smaller, they're cooler, they're dimmer, they're just using less energy, they're conserving it. It's kind of like the tortoise and the hare idea, okay? Yes, they're smaller, but because they go so steady, they make it, right? These guys are gonna burn out. You ever run a marathon or something like that? Just imagine if you were. Would you want to take off at a dead sprint? No, you're not gonna make it. You're gonna run out of fuel, right? You better pace yourself. It's the same thing for stars. They, if you want to last long, you better pace yourself, and the small ones do that. So that's all he's talking about here. He's saying these are two huge stars, okay? One of them's a little huger than the other. It goes through its hydrogen very rapidly, and when it does, it leaves the main sequence, and it's going to get even bigger, right? That's going to explain what's happening here. Here we go.
hydrogen in the core much faster than in smaller stars. Eventually, one star enters a phase of expansion and will exceed its Roche lobe, meaning that it juts far enough into the gravitational field of the other star that one will begin to pull material away from the other. This material may form an accretion disk, as we saw previously, but it can also be absorbed through direct impact, as shown here. We see the blue star acting as the vampiric star, rotating faster and flattening out. We also see that an enormous percentage of the other star's mass is being transferred in the process, actually the majority of its mass. This star is now so much more massive that fusion increases even more dramatically, which generates a stellar wind that causes the other star to become very small. Eventually, this star will go supernova and leave a tiny neutron star behind, potentially escaping the system altogether. The vampiric star will then reach a red supergiant phase where it expands immensely, after which it too will go supernova and leave a neutron star behind. So we can see that stellar evolution is much more complicated in binary systems due to the influence each star has on the other. There are so many fascinating systems out there, not just binary systems, but triple star systems and beyond. As complex as they are, many of them harbor planets. Could there be any habitable worlds that exist in such fascinating systems? What would the sky look like on these potential planets and moons with multiple stars overhead? Perhaps we will find out soon enough.
All right. Any questions over any of this? Okay, the most numerous type of star is brown dwarf. Second most numerous? Binary system. Now, if you had to go from there and you had to go on a limb, what's the third most numerous? Single, what color? Think about your graph that we had that I erased, right? Where'd you have all the dots? Well, so we said brown's the most numerous. Binary systems are second numerous. Third most numerous would be what? I drew like 97 dots, yo. The red. And then before that, after that, it would be I like graphs. We're going to do a graph, okay? Give me a second. I'm going to put this back on. Okay. Numerous. Let's do size. Right? So my most numerous are my biggest or my smallest? Smallest, the brown dwarfs, right? Somewhere down here, my least numerous is going to be my blue giants, right? Okay. I should expect things to move about like this, shouldn't I? This is very different than the HR diagram. It's similar, but it's different, right? So this would be my O-class stars, B-class stars, A, F, G, K, M, and then this weird guy over here is, I've got brown, I'm just going to write brown dwarfs, right? And then, but the other thing, right next to it, probably, is going to be binary. So combinations of these, right? Binary is going to be the most, brown dwarfs are going to be the most numerous. Binary is going to be the second most numerous. Then my reds, my orange, my yellow, down to my blues. That makes sense? It's just a visual representation of what we're talking about here. So again, most numerous type of star in the universe? Brown dwarf. Second most? Binary. Third most? Red. Then orange. Then yellow, white, blue. Okay. Now, so we have not accounted for white dwarfs and for red supergiants and all that. But right now we're only looking at the main sequence. Okay. You got anything else for me? All right. Yes, sir.
So I have a question.
Yes.
This the Alpha Centauri,
Yes.
is it also like in that class of OBAF, EKM, or?
Well, let's look at what Alpha Centauri is. I don't know its exact designation. It's a G-type star, very similar to our sun.
So are star types and star classes the same? Because there when you put binary, that's a star type, right? But also,
But it's not a class.
yeah. So when you ask the most numerous star type, you mean as in binary, white dwarf, and then like the normal stars, or because it's kind of confusing.
I understand. Yeah, I'm using this term very broadly, aren't I? I will work on refining that for next class. fair enough. It's a very good point, and I do recognize it. If I were to do a multiple choice question, and I say, what we find the most of? I'd probably write brown dwarfs, binary systems, red dwarfs, whatever. You selected that. All right. Well, y'all look pretty good.